In this lecture, we'll continue and talk about regularization in neural networks, which is an important topic to obtain good test set performance with these models. Before we start, let's review some of the questions we left behind in the previous lecture. The first question was how to know if you are in a local minima or any other critical point on the loss surface when you train neural networks. All the algorithms that we spoke about so far, backpropagation, gradient descent, all the variants of gradient descent, always had this clause in its while loop or for loop which said until convergence or until stopping criterion is achieved. What should be the stopping criterion? Hope you had a chance to think about it. We are not going to talk about the answer now, but we're going to talk about it over the course of this lecture, a little later in this lecture. The second question that we left behind was, why is training deep neural networks using gradient descent and mean squared error as cost function a non-convex optimization problem? I think we should probably spend some time here. Hope you try to answer this question and you have a good understanding of convex and non-convex functions. But let's very briefly review that before answering this question. So remember, this is a simple example of a convex function, and a convex function says that if your x-axis was here and here was your f of x axis, a convex function says, the definition says that if you have a point x1 and if you have a point x2, this is f of x1 and this is f of x2. So you have f of x1 here, f of x2 here. Then all what we say is that this line connecting f of x1 plus f of x2 will always lie above the curve. So mathematically speaking, you can say that f of any combination between x1 and x2, so let's call it, say, some lambda times x1 plus 1 minus lambda times x2. Right? So this quantity here will be any point lying between x1 and x2. So f of lambda x1 plus 1 minus lambda x2 will always be less than or equal to lambda f of x1 plus 1 minus lambda f of x2. That's the definition of a convex function. So clearly a non-convex function is one which is not convex. So a non-convex function, an example could be a surface something like this. So you can clearly see that you will find lines such as these, for instance, where the curve does not necessarily lie below the line at all times. Now let's come back to our question as to why is training deep neural networks using gradient descent and mean square error as cost function a non-convex optimization problem. One thing that you have to first understand here before answering this question is the nature of the cost function mean square error itself. Remember, mean square error, we all know, is given by, let's assume that y was the label and say h of x was the output of the neural network. Mean square error tries to minimize the square of these terms, and of course you take a mean. Half can be added for simplicity. You of course take a mean of these quantities. That's mean square error. By one look at it, you can say that mean square error will be a convex function. Mean square error is a quadratic function, which means it would be very similar to what we drew here, and it would turn out to be a convex function. Now, in this context, let's ask this question. Then why is training deep neural networks using gradient descent and mean square error a non-convex optimization problem? The reason is you could have nonlinear activation functions in your neural network that can make the problem non-convex with respect to the weights. Okay, then your counter question is, okay, let's assume now a linear deep neural network where you do not use any nonlinear activation function at all. No sigmoid, no tan h, no relu, so on and so forth. You only use linear activation functions, which is as good as saying no additional activation function other than the neural network itself. Now, would training a neural network using gradient descent and mean square error be a convex optimization problem or a non-convex optimization problem? From the answer I said earlier, it should be a convex optimization problem because the cost function is mean square error, and I just said that nonlinear activation functions is what could make the problem non-convex. So which means if you have only linear activations, it should be convex. But the answer is no, it's still not convex, or rather, yes for non-convexity. A reason for that is the phenomenon of weight symmetry. There are many other symmetries in a neural network, but weight symmetry is at least one reason. What does this mean? What does weight symmetry mean? Remember that when we talk about an error surface, we have to give an index to each weight in the neural network. That error surface has to have a certain dimensionality to it. So the first dimension would be the first weight in the first layer connecting to the first weight in the second layer. The second dimension would be that first weight in the first layer connecting to the second weight in the second layer, so on and so forth. That's how you index all your weights and you build your error surface. Now, if you take any two layers in a neural network, let's assume that these are two layers of a neural network, and let's connect them using some set of weights. It's obviously fully connected, but these are some set of weights. Now, in a neural network, in a trained neural network, what I could do now is take this neuron here and this neuron here on the second layer and simply swap them, and also swap all the weights coming into those neurons. Once again, you have a trained model, you are no more learning it, you have fully trained it. But what I'm going to do now is take a couple of these neurons and simply swap them, and also swap all the weights coming into these neurons. Will the output change? No, because the weights are the same. We have simply changed the ordering of the weights in one of the layers. But on the error surface, this corresponds to a very different position. Why so? An example is, it's almost like, let's take an example of 3 dimensions. Let's say we had x dimension, y dimension, as z dimension. And let's say we had values such as 2, 1 and 0 in these 3 dimensions. What we have done now is swapped z and y. That's what we did for some of the neurons and hence some of the weights. This will lead to a vector 2, 0, 1. 2, 1, 0 and 2, 0, 1 are different points in the 3-dimensional space. Similarly, for a neural network, if you swap neurons, after you swap, these points are different weight configurations because of the way we index them to construct that error surface. But because of the symmetry of the neural network, they would give exactly the same output, exactly the same error. Which means these two weight configurations, if, as I said, we take a trained model, which means it's already at a critical point, let's say a minimum, we are now saying that here is another weight configuration which I'm giving you, which also will give you the same minimum, which is going to be far away, because 210 and 201 are not necessarily close by in the grid. There are many points in between 210 and 201 if you plotted them in a 3-dimensional space. which means there is another point further away which also has the same minimum value of error. And this is just one swap of a neuron. For a neural network, assuming you have million neurons, you could swap a million times. So which means there are going to be that many similar weight configurations which all have the same error, which clearly tells us that the error surface must be non-convex. It's something like this. Okay? All these points have the same error. Which can happen only if your error surface is non-convex. Clearly, because there are many other points in between those minima. Okay, let's move on to regularization, which is the focus of this lecture. Let's first start with an intuitive understanding of regularization. Most of you may have perhaps covered this in an introductory machine learning course, but let's briefly review this and then talk about how regularization is done in deep neural networks or neural networks. Let's take a very simple example. Let's take these sets of values 1, 2, 3. We say that it satisfies some rule. 4, 5, 6, it satisfies the same rule. 7, 8, 9 also satisfies the same rule. 9 to 31 does not satisfy the rule. The question for you now is, what is the rule? If you observe carefully, this is very similar to the machine learning setting that we have. Imagine now that these are all data points and we are given in a training data that certain data points have a certain label and certain other data points have another label. And our job is to find out what is the model that tells us whether something satisfies class 1 or class 2. Coming back to this example, what could be the rule here which satisfies these first three and does not satisfy this set of values? A simple thought process should tell you that there are many possibilities. You could say 3 consecutive single digits, you could say 3 consecutive integers, you could say 3 numbers in ascending order, 3 numbers whose sum is less than 25, 3 numbers less than 10. It should have 1, 4 or 7 in the first column, or for all you know, you can just say yes to the first 3 sequences and no to all others, which is also correct in this particular case. Clearly, the last 2 cases would not have been the answers that you came up with intuitively. Why is that so? The reason is, even as humans, we are always looking for a rule that can generalize well if I gave you newer data points. I never even mentioned to you at this time that I'm going to give you newer data points. But still, it's human tendency to always come up with rules that can generalize well to data that we may see tomorrow. And this is exactly what we want to do with neural networks or machine learning in general. And we call this process regularization, where we use methods in machine learning to improve generalization performance and avoid overfitting to training data. So we don't want to necessarily come up with a rule that fits only the training data, but we want to come up with a rule that can do well maybe on data that we will see tomorrow, which is what we mean by test set performance or generalization performance. Sometimes even at the cost of not getting 100% accuracy on your training data set. Let's see now how we can do this with neural networks. We need one other concept to be able to follow some of the discussions in this lecture, which is the concept of LP norms. Hopefully you're all aware of this, but let's quickly review and then move forward. Remember, LP norm is formally written as LP of any vector x, let's say of d dimensions. Let's assume that x is a vector of d dimensions, x1 so on till xd. LP norm of x is given by, or also denoted by, x P norm is given by x1 par p plus x2 par p, so on and so forth till xd power p whole power 1 by p. You can make out that if you put p as 2, you'll get your standard uh, Euclidean norm or L2 norm. Similarly, you can have L1 norm, L0 norm, and so on and so forth till L infinity norm. You can actually have p to be any number for that matter, uh, any positive number for that matter, non-negative number. So you see here diagrammatically, you can see that this is how the unit ball of each of these LP norms look like. If you took the unit ball of L1 norm, it looks like a rhombus. The unit ball of L2 norm will look like a circle, and L infinity norm will look like a square. L infinity norm is given by max of a value, max of the vector, max element of that vector. This is important because this helps us understand certain aspects of regularization that we'll visit soon. A couple of points to keep in mind here is that when P is less than 2, it tends to create sparse weights, and when P is greater than 2 or greater than or equal to 2 for that matter, it tends to create similar weights. We'll see why this is the case in some time from now. The most popular regularization method for training not just neural networks, even other machine learning models, is known as L2 regularization, which imposes a penalty on the L2 norm of the parameters, which is the reason it's also known as L2 weight decay or simply weight decay. In this case, the loss function that we have for a neural network is appended by another term which has the L2 norm of the weights. This loss function can be any loss function used to train your neural network. So far, we have seen mean square error, so you can assume it's mean square error. But in future, we'll see other loss functions that you can use to train your neural network. And the L2 penalty is added to any of those loss functions. So the alpha here denotes how much importance you want to give to penalizing the L2 of the weights, and the by 2 here is for mathematical simplicity. So the gradient now of the total objective function will look like grad of L tilde of W. L tilde is the new objective function with the L2 weight decay term is equal to grad of L of W, which was your original loss function, plus alpha times W. When you differentiate this with respect to W, 2 and 2 get cancelled and you're left with alpha W. So your gradient descent update rule is going to look like Wt plus 1 is equal to Wt minus eta step length times grad of LWt minus eta times alpha Wt. Eta was a common term for grad L tilde and hence goes into each of these terms. That's going to be your new gradient descent rule for your regularized loss function. Let's do some analysis of this regularization to understand what is really happening. Let's first talk about it conceptually, intuitively, and then we'll go over one mathematical way of looking at what's going on in regularization. We just said some time back that the shape of the L2 norm ball can help you understand what you're doing with regularization. Let me add one point here that you could also minimize other norms of W in this term. You could have L1 weight decay, which is also a common approach, which enforces sparsity in weights in the neural network. By sparsity, we mean many of the weights in the neural network will be forced to go to 0. In L1 weight decay, we would say this is going to be with respect to L1 norm, and remember L1 norm of any vector is the sum of the absolute values in the vector. This is also possible. Let's try to see what would be the effect in these different cases. Remember, in the last lecture, we talked about contour plots. So you have these contour plots of your error surface with respect to the weights. We saw contour plots such as these, if you recall, which were cross sections of your error surface. Something like this. This is the contour plot of your error surface, which is the term without a regularizer. So when we add the regularizer, what are we doing? We are now saying you want to minimize over the set of weights your loss with respect to the weights, as well as some constant times your 2 norm of the weights, or 1 norm of the weights in certain cases, 2 norm of your weight square. This is equivalent to saying that you want to minimize your loss function such that your 2 norm of your weights is less than a certain quantity. You can come up with some number, there's some constant C. These formulations are equivalent to a certain degree from under certain conditions from an optimization standpoint. Why are we saying this? What this means now is the minimum of this new objective function is equivalent to minimum of this original objective function subject to the 2 norm being lesser than some value. If you recall, this is nothing but a norm ball of the weights, and it's not a unit norm ball now, it's a C norm ball. Right? A unit norm ball is when the 2 norm of the weights lies within 1, or all the weights lie within a norm of 1 around the center, around the origin. Now it's a C norm ball. It has a measure C, which it should be less than. So which means the solution here will be the intersection of, let's assume that the C norm ball was something like this. Let's assume that that's where the origin was. Okay, let's assume that here is the origin and the C norm ball is somewhere here. You can see now that the C norm ball intersects the error surface at some point, and that is now going to be the minimum of this new function, not the point at the center, because that is outside the C norm ball. So you have to find a minimum somewhere here, this one, which is a minimum for both the loss and lies within the C norm ball, which is what you're trying to do. So when you have your L2 norm, your norm ball is going to look like a sphere, and you intersect with the error surface and you get a certain solution. However, if you had L1 weight decay, then in that particular case, your norm ball is going to be a rhombus, not a square, not a sphere. So a rhombus has sharp edges, which means it's very likely that you will find minimum along points where one of the axis is 0. You can probably see this in a slightly different way too. Let's try to draw the error surface elsewhere just to make our point clear. So we want to find the intersection of the error surface and the 1 norm ball, and the intersection will typically happen at one of these corners. And what happens at one of these corners in L1 norm ball? The other weight is going to be 0. And in a high dimensional rhombus, there may be many weights that go to 0. And that's why enforcing L1 weight decay will enforce sparsity in your weights. Both are valid regularizers. In one case, you're reducing the 2 norm of the weights. In the other case, you're reducing 1 norm of the weights. But the effect can be slightly different. Let's now also see as to what we are trying to do from a mathematical perspective. Let's assume that we have an optimal solution for your original problem. Let's call that W star. So which means grad L of W star is equal to 0. So W star was our optimal solution before regularization, only with the original loss function. Let's now consider a term U which is given by W minus W star. Let's write a Taylor series expansion of loss function at W star plus U. By Taylor series expansion, this is given by L of W star plus U transpose grad L W star plus half U transpose HU, where H is the Hessian of the loss with respect to your weights. What is the Hessian? The matrix of all second partial derivatives. So you can have matrix, H is matrix of second partial derivatives. So you can have dou L by dou x, which is dou square x, or dou L by dou x, dou y, so on and so forth. Right? If you had many more weights, you can have that many. That's the size of your Hessian. Rather, if you had 1 million weights, the size of your Hessian will be 1 million cross 1 million. It's definitely a large matrix to compute. But let's move on with this mathematical discussion. So which means W star plus U is actually W. So I can say L of W is equal to L of W star, written as it is. U transpose is written as W minus W star transpose because of the definition of U. Then you have grad of L at W star, plus you also replace this U with W minus W star and this U with W minus W star. We now know that grad L at W star is 0 because that's our assumption of what W star is. It's an optimal point for your original loss function, which means we are left only with the first and the third term, and you're now going to have L of W to be L of W star plus half into W minus W star transpose into the Hessian into W minus W star. Let's take its gradient now. The gradient would be given by grad of LW is equal to grad of LW star plus W minus W transpose and W minus W together. You will have a 2 going to the power, and if you now differentiate and divide by 2 here, the 2 and 2 would get cancelled and you will be left with H into W minus W star. We already know that grad L at W star is equal to 0, which means you're going to have grad of LW is equal to H of W minus W star. Rather, going back to the previous slide's equation, going back to this equation that we had on the previous slide, let's write that out now here. Grad of L tilde W is equal to grad of LW plus alpha W. That's what we saw earlier. And grad of LW can now be written as H of W minus W star plus alpha W. Why all this? What do we want to do with this? Let's now consider W tilde to be the optimal solution in the presence of regularization, which means grad of L tilde W tilde is going to be 0, which means H of W tilde minus W star plus L of W tilde is equal to 0, because we just showed on the previous slide that grad of L tilde can be written this way. Since that's 0, this also ought to be 0. Now let's rearrange the terms a little bit and you can write it this way. Let's group all the W tilde terms. That would give us H plus alpha I, because when you add it you have to make it a matrix. So we have to put alpha I here to ensure that alpha is added to every diagonal element of H. You're going to have H of alpha I times W tilde is equal to H of W star. This means W tilde, which is a solution of your regularized loss function, is going to be given by H plus alpha I inverse H of W star. Just to remind you, I here, this notation means the identity matrix. In case you didn't get that already, this is your identity matrix. Now, in this expression, if alpha goes to 0, it's very evident that you would be left with H inverse H W star, and H inverse H is identity, or rather W tilde is W star itself. That's equivalent to doing no regularization, of course, because if alpha goes to 0, the coefficient of your L2 weight decay term goes to 0 and there is no regularization. So we are only concerned about the case when alpha is not equal to 0. What can we say about W tilde? It's not trivial to say something in general about W tilde unless you assume some form for H. So to do that, let's assume that H is symmetric positive semi-definite. Rather, symmetric is a symmetric matrix. Positive semi-definite means that the eigenvalues of H are all greater than or equal to 0. In such a scenario, H can be decomposed as Q lambda Q transpose, where Q is an orthogonal matrix. Q transpose is equal to Q transpose Q is equal to I. This should also tell you here that Q transpose is equal to Q inverse. Right? That's the only way you will be able to write it this way. So why do we do this? With this, let's try to analyze what W tilde is. W tilde from here is H plus alpha I whole inverse H W star. Let's replace H by Q lambda Q transpose. You'll have H replaced by Q lambda Q transpose and H replaced by Q lambda Q transpose. Now alpha I can be replaced by alpha times Q I Q transpose. Okay. It's the same thing because Q transpose is equal to I, and then Qi. So for example, this one alpha I can also be written as alpha I, two identity matrices, it doesn't matter. But then I we know is Q transpose. So I can write this as Q transpose, and then commutativity of IQ is QI. I can change it, and that way I'll get what I have here. This whole inverse times Q lambda Q transpose W. Now I can group the terms and write this as Q into lambda plus alpha I Q transpose whole inverse. The rest of the terms stay the same. Now A power B whole inverse is B inverse A inverse. Using that, I'm going to get Q transpose inverse lambda plus alpha I inverse Q inverse Q lambda Q transpose W. This Q inverse Q will become identity can be replaced, and hence you would have, and also Q transpose inverse will be Q itself, because as we said, for an orthogonal matrix Q transpose is equal to Q inverse, and hence Q transpose whole inverse will be Q itself. So this is what you get as W tilde. What are we doing with this? It seems to be a complex representation of W tilde. What do we want to do with it? The main takeaway here is that W tilde is connected to W star. The optimal solution of the regularized loss is connected to the optimal solution of the original loss by this transformation, the transformation that multiplies W star. Let's try to assess this transformation more carefully. If you observe here, you first take W star, multiply it by a matrix Q transpose, which is equivalent to doing some transformation on W star. And after you do that, you are multiplying by this term here. This term, can remember, lambda is a diagonal matrix. Whenever you have a decomposition such as this, lambda will be a diagonal matrix. So you have lambda plus alpha I whole inverse lambda, because all are diagonal matrices, lambda and I are diagonal matrices, you can now write this more succinctly as you take every element of Q transpose W star, it gets scaled by lambda I by lambda I plus alpha. How did we get this? we got this as one element of lambda, this is capital lambda, plus alpha I whole inverse lambda, which is what we had on the earlier slide. So this is just one term of that because this is equivalent to, so these are going to be diagonal matrices. One of these terms will actually turn out to be lambda I by lambda I plus alpha, which means every element of you first taking W star, transforming it by Q transpose, scaling it by lambda I by lambda I plus alpha, and then at the end you're rotating it by Q again. Q is again, when we say rotate, we mean it's a transformation imposed by Q on the output. Now, you're initially transforming it by Q transpose and later transforming it back by Q. So in some sense, they will probably cancel out each other in terms of the effect. But in between, you're imposing a scaling on your weight vectors, on your optimal weight vector. Let's see what that scaling means. The scaling says that if lambda I is much greater than alpha, this is going to become 1, and if lambda I is significantly lesser than alpha, this will become 0. Rather, the scaling is going to be of value only when lambda I is much greater than alpha. Because in other cases, it's going to become 0. So those components of W star may just become 0 after this transformation. So only when we have large eigenvalues, the W star components will be retained in W tilde, which is the new solution for your regularized loss. And the total number of parameters is going to be given by summation I is equal to 1 to n lambda I by lambda I plus alpha, which has to be less than n, because lambda I by lambda I plus alpha will be a quantity less than 1, less than or equal to 1. So which means the sum for all n elements will be less than n. So which means even if you had n parameters or n components of your W star vector, the effective parameters will definitely be less than the number of parameters that you had, number of components that you had or dimensions that you had in your W star. The summary here is that your original solution W star is getting rotated to W tilde when you do L2 regularization. All of its elements shrink. Why so? Because lambda I by lambda I plus alpha is always less than 1 as long as alpha is a non-zero value. Alpha, this is always going to be less than 1, which means all of its elements are shrinking, but some are shrinking more than the others depending on those eigenvalues lambda. And what are those eigenvalues? Eigenvalues of H. Remember, that's how we wrote it a couple of slides back. It's eigenvalues of H, the Hessian. This ensures that only important features get high weights and other features may not get high weights. That's one way of understanding L2 weight decay.